What's going on, everyone? This is Hoagie Hacks, and today we're looking at one of the biggest changes to Linux in the past 10 years. So, the seals that are coming to save Linux. We're going to look into a little bit of how that works with a blog that was written by Trail of Bits. They're pretty big security research, security consulting company. And they wrote a great blog on explaining how this mseal syscall works that has been added to Linux. So, we'll take a look at this here. So it says memory sealing allows developers to make memory regions immutable from illicit modifications during program runtime. When a virtual memory address VMA range is sealed, an attacker with a code execution primitive cannot perform subsequent virtual memory operations to change the VMA's permission or modify how it is laid out for their benefit. So reading this, it might sound a bit confusing, but trust me, it's not too hard to understand. So I'll dive more into that here. So this is kind of the underlying steps that are taken within mseal. This has been implemented now on Linux 6.10 and up. So first, this syscall takes in the starting address, how long this memory page is, and then flags, but don't worry about flags right now. They have not implemented anything for that. Right now it's just set to 0. So first it's going to check the page alignment here, and then on this first pass it's going to make sure that this is a valid memory page, and then finally it's going to apply this flag. I'm going to call it a flag because what's really happening is when this function is called, it takes the starting address and the end address of this memory page. And here, let's look at it here. Where is it? So it's going to go through this whole VMA structure, and it's going to add this VM flag that says that this memory section is sealed. Now, this means that, let's say you, as an attacker, have shellcode set up, right? In this, you got a buffer overflow, now you have shellcode on the stack. Typically, you can't execute that shellcode because it's set to not execute, which is a great protection, generally speaking. But someone could do route chaining, for example, and they could use mprotect to change the permissions of this certain memory space that is allocated for your shellcode that's on the stack to be executable, and then you can now bypass no execute because you can execute that that memory section. And so this is what this is trying to prevent, is that it's saying it's sealed, it has this flag, you can no longer change the permissions of this memory region. And it's also important to mention that these VMA structures that's holding the VM flags is in the kernel space. So even if you want to try to change the sealing, you can't, because 1, there's no functions to undo the sealing, and 2, unless you have system privileges, you're not going to be able to access this kernel space. So I actually have an example for us to look at to further explain what's actually going on. But before we get into that, make sure to subscribe to the channel, like and comment for more offensive security content, security news, coding, and even dive into more entrepreneurial stuff. And let's continue to the example. Yeah, so let's take a look at this. So I've got right here 2 programs, one that is going to have no sealing and one that's going to have sealing. So let's take a look at this first one with no sealing. So on this first one, you can see that I have shellcode. This is going to be on the stack because it's a local variable. And then we're going to simulate exploiting a vulnerability where we hijack the instruction pointer. So this is very common when you do a buffer overflow, for example. And what we're going to do is we're going to take a pointer to our shellcode, and we're going to call mprotect to change the memory page permissions of where our shellcode is located, because currently, since it's on the stack, it is specified as no execute, so it only has read and write permissions. However, when we do this, we'll see that we actually are changing it to be read, write, execute. So when we call exec_pointer here, which will point to our shellcode, is we're going to get our execution of the shellcode, which is, in our case, is going to call bash. So let's take a look at this. Let's run this. So as you can see, I'm bash. I'm now sk. So now what does the one with sealing look like? Well, in this case, we have a couple things going on here. Let's go to the top here. So the syscall number for mseal is 462. And we have to actually create the function ourselves this time because it's not implemented in glibc yet, so we're just calling a syscall. So we're gonna take the start address of the memory page and the length of it, just like as we saw in the blog, and we're gonna get the page size, and then we're gonna call the syscall so that with the proper parameters, with the syscall number, the start of the page, and the length of the page. Now if we come back down here to where our old main was, everything is very much the same, except before we call mprotect, we're going to call mseal on the memory region of our shellcode, and will hopefully, which it should, seal this memory page and assign the flag so that it can no longer be changed to have read, write, execute permissions from this mprotect function. So let's take a further look at this. So I'm going to separate this into two. So let's look at this during execution. I'm just going to cat this on the right here just so we have a reference. And then let's launch this up. So I'm going to set a breakpoint right at mprotect and at exec pointer. So this is going to be line 19 and line 22. And now I'm going to run it. So we can see here that we're stopped at mprotect, so all of our other code is ran so far. Let's check out where our sc shellcode is at. So we can see it right here, and if we do an x/50x, for example, of this address, we can see, like, right here is 0x48b8, that it is right here, as expected. And we can also check the virtual map, the VMA, of this address, and we can see it's on the stack, and it's read-write. Now, if I continue, so this is going to come after the mprotect. Mprotect is now being called. Now all it's waiting is to execute our function. We will see that now it is read, write, execute on the stack, which is crazy because now this will be an exploit and they'll get code execution of their shellcode. So now what does it look like for the stack with sealing? So let's clear this. And let's throw the one with sealing this time into our pwn debugger. So mprotect in this function is going to be at, there we go, at line 37. And before it gets executed is going to be at 40. Now let's run this. You can see we hit mprotect at line 37, and let's see the address of our shellcode, which turns out to be this. And just to make sure, we'll do x/50x and make sure that it's, 48b8. So all right here is going to be our shell code. And now let's check the virtual mapping for where our shellcode is hosted, which we will also see that on the stack it is still read-write and does not have execute permissions. But if we look back, we can see that before this we called mseal. So there should be a flag set for our memory region that says that we cannot change permissions. So mprotect should not work. So let's test this out. So I'm going to continue. And now we're on exec pointer, so mprotect was launched. And if we look back at the virtual mapping for our shellcode, we can see that it is still read-write, and it in fact did not pass the check that's now placed in mprotect, which checks for whether the VM flag is set, and we don't have rewrite execute, so our shellcode is not going to be executed. So based off of all this, why did we do this? Well, we did this because, one, we wanted to harden just the no execute and prevent shellcode execution, for example, on the stack, or where we know that data will be used and there will be input there, so we don't want people to allocate shellcode, for example, on the stack or in the heap, wherever it is. And then another thing is if we look back to the Trail of Bits blog about mseal, is another big thing is mitigating unmapping based data only exploitation. So what this means is actually part of how mseal was created was because of something that Chrome discovered. So Chrome maintainers rationalized an easier and more powerful technique with the added benefit of circumventing control flow integrity. They determined if an attacker can pass a corrupted pointer to an unmapping/remapping syscalls, they can punch a hole in memory that could be refilled with attacker-controlled data. This would not violate CFI guarantees, as forward and backward edge CFI would cover only tamper-control flow situations. So, like it says here, this is enticing for browser implementing just-in-time compiler because it switches between read-write and read-execute permissions a lot. And it even goes into a real-world exploit, which I'm not going to talk about here, but you can check out Trailbit's blog. So that was the main goal of mseal, is just so we have better control over what we are assigning to memory in terms of like what is allowed to do what. So having execute permissions on certain things, having read-write permissions on certain things, and just sealing that in the kernel space so it cannot be touched. Now, this implementation of mseal also had a lot of debate. I'm not going to go too far into it, but if you've ever heard of Linus Tech Tips, he was actually completely against it. You can see here, he says this is all completely nonsensical from Linus. He was like, no more random code, no more random seals, none of this crazy, blah, blah, blah. So definitely check out this discussion because it's kind of interesting. It's between him, some people from Chrome talking about just the future of what mseal is going to look like, and especially since I think I can show you guys here is this hasn't been done yet, I don't believe, but it's going to be in sometime soon implemented into glibc. So instead of having to directly call a syscall like we did in our program, it'll just be in mseal, and especially for something like Chrome, which for securing Chrome. But they said it also would be good to have support in like a GNU-C library. Yeah, so that's all for today. I hope you guys enjoyed the video. I'm going to be talking more about security news, offensive security stuff, coding, and even dive into a little bit more entrepreneur stuff and like my background. And I'll see you guys in the next video. Peace.